So first question, anybody using Redis? Oh wow, a lot more than I thought. Okay.
We own Redis, so it's actually a pivotal
That's true. Yes, sometimes I forget.
It's kind of like I think it's one few guys out there somewhere in the middle of nowhere. It's kind of like one of those little hidden gems that technically we have the committers on payroll, but.
So what about BloomFilters? Okay, a few. All right, so first about me. I'm Chris Curtin, head of technical research at Silverpop, an IBM company. It's been 14 years since I started at Silverpop now. I've been doing technology stuff for about 25 years. And we built a SaaS platform before people called it SaaS. It was before they called it multi-tenant. But we were in an industry where, at the time, we sent email. So being able to put a platform together to make it easy for our clients to send email cheaply, we came up with a SaaS environment. Prior to Silverpop, I did real-time control systems, factory automation, food safety. So I've got a background both in business and in ways that people can use technology to kill people. And what my group does is we look at interesting technologies, figure out things that are applicable to where our business is going, but also, since Silverpop's been around for so long, things that make what we did for the past 14 years better. We won't say everything we did in the past was wrong, but there are things we look at today and go, wow, I can do that so much better now. And we're going to talk about one of them today. So first, open positions. We're looking for a technical lead, a couple senior engineers, an architect, and automation engineers. We are an agile shop. We are also heavily pushing towards a DevOps world. Not DevOps in the Amazon way where product owns production, but to the point where we sit down with ops almost every week at stand-ups to talk about what we're doing, what they could impact in their systems, what we should be doing to make it easy for them to manage our systems. So we also have QA automation engineers because we got a fairly large product. All right, so first I'm going to talk about Redis. Then I'm going to talk some about BloomFilters. Then I'm going to talk about this idea of failing fast. To be clear, I'm not going to talk about the fail it fast like you hear in the Valley of I have this wonderful idea, give me $1 million. Oh, I've got $100,000 left. I'm going to pivot. I failed. No, this is about failing fast from a software point of view. How do I not take resources that are very expensive, query them or call them and find out that there's actually nothing there of interest, but I still had to pay the cost to go make that call. All right, let's start with Redis. So first I'm going to talk about what it is. I'm going to tell you why we started looking at it. We're going to go through some basics. I'm going to talk about the concurrency. It's going to feel very 1990 until you realize the simplicity is what makes it so awesome. I'm going to talk about some operational considerations. This is a great technology, but when your ops guys look at it and they start Googling around for ops in Redis, they're going to see a lot of people concerned about the way that Redis is being abused. And lastly, I'm going to talk about some challenges and give you guys a demo of replacing a JMS queue with Redis. So let's get started. Hate to read off the slides, but here we go. From redis.io. It's an open source, BSD licensed, advanced key value cache and store. It is often referred to as a data structure server. And that is a key part of what we're going to talk about today, this idea of a data structure server. It contains strings, hashes, lists, sets, sorted sets, bitmaps, and hyperlog logs. Anybody know what that last one is? So this is one of the reasons we got into this. Hyper what? So hyperlog log. It's this idea of being able to do a counter in a very small amount of memory for a given error rate to figure out populations. So if I wanted to keep roughly 1 million items and be able to query this thing and says, is this key in there? I can do it in 16 kilobytes with 99% accuracy. The problem is, go to your product folks and say, hey, I'm going to use a structure that has 1% inaccuracy. Yeah, that's not going to fly. So we had to move on from hyperlog log. And this is before they implemented it in Redis, but we spent some time looking at it because that's just too much loss for what we do. We're going to talk in a little while that we are interested in 0.1% error rate. Product took a little while to get their head around it, but I think we've got them convinced that 0.1% error rate or a false positive rate is okay for the things we're going to do. Okay, so features. What makes this really interesting is the data actually lives on the server. As a client, you send it commands. It does things to the data store, and replies back almost like you'd expect in a web browser to server communication. I ask it to add something to a queue. I ask it to pop something off of a queue. That queue might have 100 million things in it. I'm not worried about bringing it back to my memory space. I'm not worried about reading it, changing it, putting it back. I say manipulate the data structure that's on the back end. Has some very interesting pub/sub stuff. I know, pub/sub, I mean, that was, what, 10 years ago everybody was super excited about pub/sub? But they presented some interesting use cases here to make it easy for you to listen on queues and wake up a worker to do something when basically something's injected into a queue. Kind of like JMS, kind of like most message queuing systems, but it's very, very simple. Time to live on keys. So this is a challenge we've got today with our Oracle databases. We set something to only be around for a day because we don't care about it tomorrow because we've either rolled it up or it's no longer relevant. Well, guess what? The DBAs still have to have scripts that rip through and blow away all that data, all the undo, redo, all the challenges with that. Redis, you set a TTL on it, and it has some background processes, very lightweight, that take out those keys and they just disappear. So the overhead of cleaning up possibly tens of millions of events a day is almost no cost because of the way Redis structures it. It now has clustering and automatic failover. When we talk in a few minutes about some of the advanced stuff, you'll see that it used to not, and this was a big challenge for us in adopting it, because even though it's nice to have a data structure that I don't care about tomorrow, I still need it for the rest of today. Anybody ever heard of Lua? Okay, that surprises me. Wow. Okay, so for the people in the video, about half the people in the room raised their hands about Lua. They let you write Lua scripts directly into Redis to do some stuff. Not quite stored procedures and all the negative that comes with stored procedures, but it is nice for a couple of very specific use cases. And another thing is there are client libraries for any language you can think of. C, C++, Fortran, because apparently somebody in the scientific community loves this. There's a Fortran driver for this. He's laughing, very well taken up in the community. So why did we start looking at NoSQL? Remember those operations guys I talked about before and how we're becoming a DevOps shop? Before we were bought by IBM, to be clear, we were looking for ways to not buy Oracle licenses. Oracle is great for where we use it in certain places. It is very powerful for the redundancy, for some of the stuff we really like to do. But we're doing stuff in Oracle because we had Oracle. And it was not efficient, and it was expensive. So one of the ops guys goes, so for the cost of an Oracle Enterprise license, I will give you 64 cores and 3 terabytes of memory. What can you do? So we went off and thought, what could we do? We spent some time looking at the DBA logs of where were we spending our time. Where's our I/O? Where's our CPU? What are the specific tables that we beat the snot out of? How much of the data that's being replicated to the DR center is transactional stuff that we don't care about 5 minutes after it happens? Then we started digging around and said, you know, we've got all this stuff that we do in queues. We've got all this stuff that we do to go distributed, to go wide, to be able to run thousands of threads if we want to. That the only reason we talk to Oracle is because it's got a really good sync point. I can get a lock and make sure nobody else is stepping on my data. That doesn't need to be in Oracle anymore. So basics. It's an in-memory only key value store. If it doesn't fit in memory, you can't use Redis for it. That being said, for the cost of an Oracle license, I'm getting 3 terabytes of RAM. Yes, terabytes of RAM. So I'm not that concerned about whether or not my data set's going to fit in memory here. It's single-threaded. Yes, it is single-threaded. There is no concurrency. There is no locking. There is locking. Redis accepts the first request, and nothing else happens until that request finishes. Now you're thinking, wow, that's really 1990s, 1980s, 70s. But the simplicity of what this tool is going to offer to you makes that not a problem. Especially when, for the cost of an Oracle license, I can get 64 cores and 3 terabytes of RAM. Basically, you run lots of instances of Redis, because if they don't have to talk to each other, why put them on the same machine? Again, go back to the relational database world. You had the relational database, and it was what you used because that's what you had. You don't need to do that anymore. No paging, no reading from disk. You run out of memory, bad things happen. So you got to, operations again, you need to be paying attention to what you're shoving in here and be able to get alerts to say, hey, we're getting pretty close to our memory limitation. Because it is bad when he hits memory. Basically, CS 101 data structures. Anybody actually have a computer science degree? Because okay, good number of them. I get to say that because I was one of the youngest people to get a computer science degree when I got mine. Everybody else was either way older than me or way younger than me. And most of the engineers I've met who are around my age don't have CS degrees, they have EE degrees, or they have computer systems engineering degrees. But that's basically computer science 101 data structures. We all remember that: push, pop, queue, list, hash. Tens of millions of keys in this thing is not a big deal. So this idea of I'm just going to create a key, stuff something into it, let it live for 5 minutes, and have it disappear is not a problem for Redis. And I said before, how much RAM defines how big of a data store you can get. There are ways to tell it to only take a certain amount. So you can bring up a Redis instance and say you've only got a gig because I've got 12 other instances on this physical machine and everybody's got a gig. Or you can say, go crazy, take as much as you want, although I wouldn't recommend that because, again, while memory is cheap, there are definitely some concerns when you get up into multiple gigabyte data stores. Basic data types, like I said, strings, hashes, lists, sets, and sorted sets. Again, CS 101. This is so simple, and the simplicity of the design is something that you will read about every time you go and look at a web page about Redis or you read an article about it. They talk about how simple it is. And because of how simple it is what makes it so useful. So hashes. Basically, a hash is a collection of key value pairs with a single name. Useful for storing lots of stuff together that I can reference by a single name out in Redis. Only problem is it can only be strings or numerics. I can't do data structures within a data structure. And a lot of people have asked why, and the guy who basically is the architect of this says, well, you can do everything else. In the primitive data structures, I don't need to make a bigger data structure. You just need to keep your key management. We'll talk about key management in a bit. Let me give you an example to make sure our internet connection stayed up. So here is a Redis request to get a value out of a hash. Oh, by the way, if any of you write APIs that you publish, go look at this site. Look at how they run an instance of the tool inside of the API. I'm sorry, inside of the documentation, so I can go and play. So for example, my hash, I can type field 1. I'm talking to a Redis instance right here. This is on the web. If I want to try something, I don't have to figure out how to spin one up. I don't have to go get hardware. It's an awesome idea. Anyways, back to this. So the hget, basically get me the value of a hash. Look at this. In every single method in the API, the commands that they call them, he talks about the big O notation for the use of this command. Now, big O wasn't CS 101. I think it was 3-something when I got my degree, but they spend so much time on making sure that these algorithms are as efficient as possible and that you understand when you're using one what the complexity is. So here, O1, basically just based on the size, the number of elements you have in the data store is dependent on how fast you're going to get an answer back. When I jump to pick something else, now I figure's the one I grab. All right, eventually I'll show you one that isn't O1, but he does talk about log n and again, basically data structure, computer science, and talk about the performance of these things. Where'd you go? There we go. All right. Sets and sorted sets. The idea behind a set is you throw something into it. Redis makes sure that there's only one of them, and you can quickly get access to counts and sort them and get them out, get specific elements out. It's a basic set. Sorted sets are interesting. The idea behind a sorted set is you can associate a weight with a key in the set. So for example, URLs that you're crawling. How many times have you seen a specific URL? You continue to increment the count in the sorted set. And then you can, using the zrange command, say, give me the top 10 items in that set. And because he's been storing it in data structures that are optimized for doing selection, you get that answer really, really fast. There could be millions of elements in that set, but you get the answer really fast because you've been storing it in a sorted set. Let me show you what that looks like. I blew this up so you guys can see it. Can you guys see this in the back? There we go. Right. I'm sorry? Z-add? Oh, okay, thank you. But here's an example of finding the scores, the top 3 scores, based on the values that I added. And here's one, O log n plus m. Oh boy, those are some brain cells that have been long dead to remember what that means. But again, based on the size, it's a logarithmic algorithm to go figure out what the top n elements are. So think about a problem that you have today that you are dropping into a relational data, the data into a relational database in order to do an order by, to be able to do something to get you the top n. If you don't care about it for any reason other than the top n, or that you're storing it in such a way only because of the top n, stop using a relational database. Start putting it into Redis. Because in an hour, this may not matter anymore, and if you drop the keys, so what? But you haven't done the hit of the DBAs, or the things that DBAs are going to hate you about. Any questions so far? All right. Lists. These are the things that we found the most interesting. It's basically a queue. Left push, right push, pop, insert into a certain position, pop n. And when you think about a lot of the things that you do in your business applications, it is about dropping something into a worker queue, dropping something into a database to be picked up later, dropping something into a database element so that you can control who has access to it. Lists make that stuff easy. So for example, we can push a value, JSON, because it has to be a string, it has to be a primitive, into a queue and have a worker that's sitting on the other side waiting for something to show up. And when it shows up, pop it off and start working. Now, I'm going to do a demo in a little while that shows an implementation of JMS. But when you start to combine lists with things like Akka actors, true multi-threaded environments that can process thousands of threads and that are all popping work off of something, think about a JMS queue. What's it backed by? A relational database, right? If you want to do any kind of persistence, you've got something behind it that is probably a relational database. Go ahead and put it into Redis. Then you don't have that overhead. I will show you an example of blowing a couple 100,000 rows of data into Redis and popping it out with multiple threads in a few seconds when we get to that part. Concurrency. We talked about being single-threaded. When you submit an operation, you can work on a single key, or you can do a relation between 2 keys. Give you an example, they have this thing called rpopl push. Right pop, left push. So I have a queue, all the work to be done. I have a list, which is what my particular thread will be working on. Atomically, I pop off the queue, drop it into my list, and I now own that. It's atomic. If something goes wrong, there is not a message lost. There's not a rollback that happens. Redis guarantees that it is completed when the call returns. Pipelines are the answer to people going, yeah, but I've got a couple things that are dependent on each other. I really want to lock. So the idea behind a pipeline is that you can submit multiple commands from the client, and Redis will basically grab that single-threaded lock and execute each of your commands and return. Now the challenge with that is there's no way to do logic between them. So if your logic is already figured out where you know you're going to push from this queue to this queue, and then you're going to do it again and again and again, great, go ahead and submit a pipeline. But if you're going to pop off and you need to look at the value and go, oh, this is a event of an open or a click-through. Oh, I need to drop it into that queue. You can't do that in a pipeline. Instead, you use a Lua script. So Lua lets you actually write code that runs inside of Redis while your thread or your request is holding the Redis lock. Of course, the problem with that is if your Lua script starts to do some weird stuff, you've blocked everybody else. So be very, very careful what you do within a Lua script. Any questions so far? All right, let's look at some code. First, I'm going to show you a pipeline. Whoops. Oh, we shut down. I apologize. I closed the windows before. When we were trying to get the projectors up, I had to reset. I forgot to reopen this window. Yeah, I'm going to do that in a second. Actually, what was the file? I'm usually more prepared. So Redis, BloomFilter Redis 43. BloomFilter Redis 43. All right. So here's an example of a pipeline. I basically say I want to start a transaction. Here's all of the requests I want to do. And until I actually call exec, nothing happens in the client side. I'm sorry, in the server side. He builds up the message, goes ahead and shoots it off to Redis when I call exec. And that's basically what the UI, the API looks like for Redis, for the drivers. It's the same commands that we saw before. What key we're talking to. In this case, what key we're operating on and what the data is. So I'm setting in this key, which is a hash, this element to this value. It's that simple. No building result sets, no building objects that I have to try to figure out how to encode properly. It's basic commands, integers and strings. Now let's look at a Lua script. Just one thing I don't like about this laptop is it gives me grief when I try to open multiple windows. Whoops. Why won't you go full screen? There it goes. So here's an example of a Lua script where the argvs, just like every other language, argv is the vector that gets passed to the main. You pass in the keys that you want to do. Within a loop, I go ahead and call get bit on a particular bit. If it's set, this is where the logic comes in, I then call set bit on it and set it to 0. So in this, what I've done here is I've written a script that runs inside of Redis so that nobody's messing with those bits when I'm trying to get and set them. It's very efficient. It doesn't do anything that could go off the rails unless that turns out to not be a valid value, at which point the loop will run forever. So we probably need a check in there to make sure that low doesn't lead for an infinite loop. But anyways, it's a pretty decent example of what a Lua script looks like. Questions? All right, so operational. I said Redis only fits in memory, but it does have the ability to persist data, so on startup, it'll come back to your current position. There's 3 kinds of persistence. The first is none, which means on restart, everything's gone. We don't write anything to disk. We don't do anything. So for certain data structures, that might be okay. The second is what's called a journal or AOF, where for every event that modifies data, they write an event to a log. And when you start back up, he replays the log. And the third is a point in time, called an RDB. While point in time is default, very few people actually use it because it can get tricky. What it does when it comes time to write that RDB is he actually will fork. And if you guys know what a fork at a Linux kernel level does, it makes an exact copy and then writes the exact copy to disk. Well, if that exact copy is 10 gigabytes, it's going to take more than a few milliseconds for that fork to happen. And when that happens, everything stops. So we are running AOF, and in a few places we've talked about going to none. Yeah? Do you know if it's a fork or default? I don't know. I just know that it's one that if you've got a pretty decent size memory footprint, they tell you not to use it.
Yeah, one of those system calls has copy on write semantics, so
that's what I was getting to.
It shouldn't actually copy, but maybe they copy so that it has transaction basically, so it's isolated.
I bet you if you go out there to the Redis mailing list, it's a Google group, if there isn't a dozen articles, you can post a question, and the guy's name is Interas? Do you know? Something like it. Yeah, so the gentleman is very responsive and very involved in the community. So if you ask questions, if the guys who are helping him build this don't answer it, he will usually chime in within about 24 hours. So optional master-slave replication. So if you want to do slaves for failover or for high read loads, go right ahead and do it. Remember I mentioned before that there was something about the way that Redis was doing HA that we didn't like, that we were a little nervous about going after. They decided to grow their own. And in this day and age, growing your own HA just seems wasteful. You got Zookeeper, you got Mesos, you just go look at the way Yarn is implemented. There's so many people out there who've solved this problem. So we spent a lot of time watching before we decided to use this tool because we didn't know where this was going. Well, the guys actually the team that implemented, it's called Sentinel, made a really strong case for why they didn't like Mesos, why they didn't like Zookeeper, why they didn't like the others. We spent a lot of time looking at their arguments and understood for this kind of structure, those other tools didn't make sense. So Sentinel, which is their implementation of an HA platform, which is now GA, is pretty robust. We've been pretty impressed with what it does, and the people who are using it in bigger production environments than us online talk about failovers and not having problems and it working correctly. But we were very uncomfortable for a while about why they thought it was necessary to grow their own. Common deployment model. Go back to my for the cost of an Oracle license. Lots of instances per machine. Because in many of these cases, you don't need to have the data in any way related to each other. So bring up another Redis instance. Yeah?
Regarding the multiple instances, do you usually pin the threads to CPUs?
So the question was, for the folks on the video, do we pin the processes to a CPU?
Like that thread of pin?
Yeah, we have not. We've been watching it because we haven't had a reason yet. We're not near that volume. There's a lot of discussion on the user groups about whether tying to a core is definitely bad because he does have some background threads doing stuff. But tying to a CPU, if you can, for some folks helps. We've not done anything to say whether it's good for us or it's worth the risk of taking a core that doesn't do anything because that particular set of shards isn't getting hammered. But it is something to think about as you're planning your deployments. So the approach we're taking is a couple machines. We don't have the 64 cores yet, even though that's what they told us that they could get us. We have a couple machines, there's 3 machines, master slaves, 2 slaves. The master and slaves are distributed between the 3 machines for each of the databases. So it's not all of the masters here, all the slaves here. For the different instances we're running, we've got them spread all out. We are huge DevOps and Chef users, so this is all automated. When the server crashes or gets rebooted or whatever, the Chef stuff knows how to rebuild it as the correct thing. Tell Sentinel, hey, by the way, I'm back, make me the master again. Millions of keys gets really hard to manage. Think about it if you wanted to pop in and go, so what is in queue import client 99? If you don't know what that's called, there's no good way to find it. So we've spent a lot of time thinking about directory hashes for ops. A well-known name that contains a hash of all of the keys in Redis that is associated with that particular service. So ops can monitor that key. If the key disappears, something's wrong. Or if the key gets above a certain size, something's wrong. And they don't have to worry about us creating worker threads all over the place and having to worry that they're monitoring the correct worker threads. They monitor these directories in the hashes. As I said before, operations, you'll see online that a lot of ops people have issues with this because of the key explosion. If you think and plan and do these directories, ops will be really happy with you. Plus, then you can do a whole lot better monitoring of what's going on in your production environments by building these structures. Questions so far? All right, so some of the challenges we had. Key explosion. You've got a single namespace, so it blows up quick, especially if you've got the idea of, well, we're going to shove stuff into a little queue. So these 5 things that this thread's going to work on, we're going to create a queue just for them. And when it's done, it disappears. That's great. But when I have 100 threads doing that, suddenly I'm into thousands of keys, and then it explodes. So spend some time thinking about how you're going to structure your keys. Lua scripts. Don't use them if you don't have to, because you block everybody else on that particular instance. Now, there are some things where it makes a whole lot of sense that you don't round trip. Why do a round trip back and forth, even though it's really fast, to do a check or to know which other key to go feed from? So Lua scripts are useful, but be careful. Pipelines also can block, although in reality, you've got to write a really ugly piece of code to have a pipeline that does anything that would block other people. Because all you're issuing is commands. You're not doing logic. So all you can say is do this, do this, do this. And unless you're saying 1,000 or 10,000 do thises, it doesn't really hurt. No nested data types. I really want a hash of lists. We came up with some great use cases that if we had a hash of lists would be great if I could atomically move between any number of lists. But he doesn't support it. And he's made some strong arguments as to why he won't. And without namespaces, be very careful how you name your keys. We're not a huge organization, and we've already had problems where this group has decided to use this naming convention, and this other group did something close or pick the same naming convention, and they step all over each other. And unlike a relational database world where if the table already exists and you go to create a new table, it blows up, if the key doesn't exist, Redis will create it. And suddenly what you thought was a list turns out to be a hash, and stuff starts blowing up, and by the time operations goes and looks, the key doesn't exist, so they don't know what the heck just happened. So naming a namespace is something you got to be very careful, or a naming convention is something you got to think about ahead of time. Questions so far? All right, concurrency. So I'm going to show you an example where I have a client that does a real simple L push, a consumer that runs a bunch of threads, does RPOPL pushes. And the idea behind this is I've got a work queue. I have some number of workers. In this case, there's only going to be 5, but there could be thousands of them, that pop the head off of it, assign it to themselves, and start working. And the reason you assign it to yourself is, remember we talked about those directories for ops? Ops is monitoring that directory to say what are the workers that are out there, and what are the queues they're working on. And every couple minutes, they go through the directory, go and make sure those keys exist, or if those keys exist, look into the data in the keys and make sure that the thread isn't dead. Because when you have lots of threads running out there, especially in Akka, you don't really get alerts that things have gone wrong. So ops will see, hey, wait, this key has existed now for more than a minute. There's something wrong. We need to start digging. Versus I've got thousands of threads, all of who are blowing events all over the place, and ops gets overwhelmed. And when the worker is done, he says, I'm done. He removes his queue because he's done with the data, and we keep looping. Any questions? I'll show you some code now. Oops, I hate this mouse. Hello. All right, so here is the consumer. Basically, every 10,000 events that he processes, he's going to spit out something that says, hey, I read 10,000, and this is how many milliseconds it took. He's doing rpopl push off of the queue into his own queue. If there's nothing there, he goes to sleep. The only reason he's going to sleep is trying to get two multi-threaded processes to start at the same time on the same laptop is kind of a pain. So I give myself half a second to get the client to launch. And then when he's done, he clears his worker queue and loops back around and does it again. The producer is as easy as that. I'm sorry, the producer is similar to that, where he starts a pipeline. R pushes 5 things into the queue within the pipeline, syncs it so it gets processed, goes and does it again. And again, I had to restart, so my world is not going to get set up here.
What's the reason you use a pipeline?
I just wanted to show an example of doing multiple requests. And this finished in the time that I got back to answering your question. So let's go look at, here's the client. So basically, he created 10,000 multiple threads, each created 10,000 events into the queue in 55 milliseconds. That's all running here. We see very similar performance, including network latency, in our production environments. So Redis is blindingly fast. Now, the consumer, because he's only working on an item at a time versus the producer was blowing 5 items at a time into the queue, he's taking 166 milliseconds to read 10,000 out. So yeah, this isn't really a benchmark, but the idea is we are just running flat out, reading and writing in and out of Redis. And it is very, very fast. Yes?
What's the actual transport protocol from remote client to server?
So the question was, what does the actual protocol look like between the two? It is a binary protocol, and that's about all I know. I've not had a reason. Yeah, it's TCP. Yeah. I've not had a reason to have to go look at what the protocol is doing underneath the covers. And if you're interested, because there are so many ports of the drivers in different languages, they're all open source, and you can go take a look at them.
Do you know if there's support for like things like that would seem to be something that would be very helpful in this case?
The question is there native stuff for InfiniBand and stuff like that? I have no idea. I'm sorry. That's not our environment, so I haven't had a chance to look at it. Any questions? I mean, I just built an app that could replace your JMS queue. You blow up the box. You've still got the slaves out there, so you didn't lose anything. I made a really simple client or consumer that just reads the messages off. I was going to do an Akka one, but Roy is doing an Akka talk in a month, and I didn't think you guys would want me to stand up here and talk about Akka the whole time if he's going to be here in a month. It is really that straightforward. Question?
So there aren't strong consistency guarantees because the slaves are written asynchronously. So if you blow up the box, there is a potential chance of data loss. It's actually reported straight on their site.
Yeah. So I get to the guy in the audience's comment, it is an asynchronous sync between the masters and the slaves, so there is a chance you're going to lose something.
Yeah, if there's a partition between the two, it's higher.
Yep.
So if there's any partitioning, it goes up very quickly.
Yeah, so if you've got a problem with partitioning between the masters and the slaves, but you've got that with JMS too. You got that with almost any of the queuing technologies.
It comes down to if they wait for a acknowledgement from the slave before acknowledging for the client is the place where they have a lost chance there. They acknowledge to the client prior to getting acknowledgements from the slaves.
Right, yeah, so the gentleman in the audience was talking about what the challenge is with the way that the protocol is written today. Any questions about this before we move on? Yeah. Yep. Yep. Yeah, because I wasn't sure if we were going to have networking, so I made sure it was all local. I was gonna. Yes, especially when you got 10 gigabit between each of your servers, which we do. It is stupid, especially if you don't have to do if you're either doing AOP or no persistence, where you don't have to worry about the disk at all, it is very, very fast. Which again, when it's single-threaded, you're like, oh God, this is like the 80s all over again. But this is so fast that it doesn't matter. To Gunnard's comment when he was talking earlier about using Redis for a cache store, we found we added 5 milliseconds to the amount of time it takes us to store in Redis or retrieve from Redis a Tomcat session than if we left it up to Tomcat to do pure in-memory synchronization between 4 nodes. 5 milliseconds. We don't even see that in the load tests. The only reason we knew it was there is because we wrote a specific test to figure out what was the latency that we were doing to Redis. And that was in a production environment. Any questions? Cool. All right. So talked a bunch about Redis, and okay, that's kind of cool. It's a neat toy. But this talk was about fail fast. And now we're going to get into how we make use of some Redis stuff to fail fast. So BloomFilters. We're going to talk about what they are. Again, why we started looking at them, because while this is a pretty awesome technology, we've got to have a business reason to go play. The basics of them, about false positives. We're going to talk a lot about false positives. Some example use cases, and why you really don't want to do this in a database. All right. I'm not going to read this, because the Redis one was a couple key things I wanted to point out in this, but this one, you guys can read it. Wikipedia. I was working on these slides while I was helping my 16-year-old with homework, and when I go and look up stuff on Wikipedia, when I help her with homework, she goes, we're not allowed to use that. So don't tell my kid's teacher we took a definition out of Wikipedia. All right, so the idea here, you take a key, you apply a hash to it, some number of hashes, and you get a bit that you need to set in a bit set. So if I've got 7 hash functions, and I hash my email address, each of the hash functions will give me a bit number between 0 and some stupidly large number. Those 7 keys should be enough to uniquely identify my email address without having to know what my email address was. Okay? Mathematicians have proven this thing out. There are people who write theses, and there's a lot of cool stuff up there about this, theses about why this works. And I will show you in a second an example of how we size it, but let's look at an example. So I've got 3 keys, X, Y, and Z, and I hashed them all using, in this case, just 3 hash functions. And each drops into a particular bit element. So if you'll notice that this one and this one both match to red and purple's Y and Z. But they didn't match all of them. And that's what the magic of this is all my hash functions, the chances of all, in this case, 3 hash functions, hashing 2 keys exactly the same is incredibly remote. It still happens, and we'll talk a lot about that in a few minutes, but it allows me to build this data structure. And now when W comes along and I need to look them up, is W in the set? On the same 3 hashes? Maybe. Maybe. Nope. As soon as I saw a 0, I knew W is not in the set. I know whatever I'm building this Bloom filter over, W is not part of it. So think about some use cases on that. How quickly can you go, oh, it's not in the set. I don't have to go to the database. I don't have to worry about X. I don't have to do Y. But there are false positives. Building perfect hash functions is possible, and we'll get into CS grad school stuff to really talk about what a perfect hash function is, but they're just not worth the cost. Yes, I could sit down and spend some time and figure out a perfect set of hash functions for my known set of email addresses or my known set of URLs, but it's just not worth it. So what the algorithm is, and I'll jump to the example in a minute, says is you tell me what your acceptable false positive rate is, roughly how many elements you think you're going to want to shove into one of these, and I'll tell you how many bits and how many hash functions. And let's go take a look at that. Okay, math. In this example, I want to put 1,000,000 elements with an error rate of 1 in 1,000 into a Bloom filter. I need 1.7 megabytes, and I need 10 hash functions to store 1 million items. Try to do that in an index in a relational database. Try to be able to ask an index in a relational database if a key exists this quickly. It's not possible. But false positives. You really have to be able to explain to your business folks and possibly your end users what happens when I do hash, because it's going to happen. We're not putting a lot of effort into making sure I have perfect hash functions, so there is a chance I'm going to hash. I'm going to hash a key to something that, to the bit locations that exist for another hash. So you have a false positive. Yes? So exactly that, a number of hash functions. So I'm going to take my key, my email address, my ccurtin at Curtin Home, and I'm going to apply a CRC32 to it. I'm going to do a LV something or other to it. There's like almost 2 dozen functions that mathematicians have figured out to say, apply a string, use this method, and we will give you bits that we guarantee are unique for that key that came across. Yeah, it's in the 20s, although if you ever bounced up against that, I'm sure you can find other hash functions that weren't implemented.
The other thing too is you use the same hash function. Some hash functions have seeds that can be altered, and that's usually a way that some of them do it. They just put a different seed in. So like you go from 13 to 17 to whatever.
Oops, I lose my connection. Here we go. So for example, to go to 10 million. So now instead of 1 million elements, I want to track 10 million. I need 17 megabytes, and I still need those 7 hash functions. So I went up 10 times my data size and did not change the number of hash functions I need. You're probably going to need to get into 100 million, 200 million before you start running out of the core set of hash functions that the mathematicians and the guys who do PhDs on this stuff have recommended for use here. And most of these are implemented in extremely fast algorithms or code. So you don't write these hash functions yourself. You just pick somebody else's hash functions and use them. Again, you could go back and write perfect hash functions. I don't recommend it. Just use something somebody's already written. So back to false positives. So what a false positive is we've hashed a key that just because of the way that the hash functions worked matches, say, this, and that. You'll notice that none of the keys up there had all 3 of those. But when I hash my value, because of the keys that were added beforehand, somebody has set the bits. So when I ask the Bloom filter, hey, is this key in there? He's going to do all his hash. He's going to come back and say, yes, it is. But it's not. That's called a false positive. So you need to think through your use cases and say, what is the scenarios where if I find out, if I'm told yes, it's there and it's not, that I either do or don't do something? And how acceptable is that? In a lot of cases, you can build a filter off of something that a false positive doesn't matter. I'll give you some examples in a little bit. Or you can use the fact that something is in the hash, in the Bloom filter, as a reason to go do something expensive. And that expensive thing may come back and say, nope, it wasn't there. But the fact that you did not do 1,000, or whatever the number, 1,000, because our 1 in 1,000 error, 1,000 lookups, because the filter said, no, it's not in there, that 1 is an acceptable cost. Does that make sense? All right, cool, because there were a few people who were like, creation. There are libraries in every language I looked up to create these things. Mathematicians love them. Network guys love them. Ad networks, banner ad guys love them. So there is a library, including JavaScript, because we're thinking about doing Bloom filters in JavaScript, to build these things. So don't do it yourself. Sometimes when you create these things, you're going to build them in memory for single use. So an example of that is I'm going to build a list of people who are currently in my database, and I'm going to take the list of people who just went to my trade show, and I want to go ahead and add them to the database. But because I don't have a good upsert command in my database, say it's Mongo, it's Cassandra, it's HBase, something like that, I don't want to do a massive lookup of 1 million on the left to 1 million on the right. So I build a Bloom filter of the 1 million on the left, take the 1 million on the right, and keep hitting. And anybody who is not in the 1 million on the left, because it's a Bloom filter, it's a very fast lookup, I go do the expensive operation of adding them. Now I may have a key violation because I may have said, oh, you're already in there. I'm sorry, back up. I may have a false positive which says, hey, you were in there. So we're going to take the people who we think are in there, we're going to drop them into another structure and check them again later. The idea is I hit my false positive, I go, I can't throw this away. The business guy says, I want you to try him anyways. So we're going to take him offline and process him separately. And the idea here is a very expensive operation, if I don't have an upsert, is now something I can batch, is now something I can do offline. Meanwhile, I can process 999,000 of those folks that went to my trade show. That'd be a hell of a trade show. Without having to worry about very expensive database operations. The ad networks used to build these using Hadoop. So they would take all of the activity from yesterday, the fact that the billion-something ad impressions that they placed yesterday, rip it through a Hadoop cluster, and build a Bloom filter of what ads you saw. So a filter per ad per cookie. They would then take those, read-only, load them up into a data structure, and query the heck out of them. Did you see this ad? Because you just showed up on the website. Did you see this ad yesterday? Yes, you did. OK, I'm not going to show you that. No, you didn't. Here comes the ad. Billions of impressions being handled in, depending upon your error level, 2 meg of memory, 3 meg of memory per ad. I mean, it's a pretty useful structure. The in-memory stuff is great when you're doing lots of reads. Or, sorry, it's read-only. Or when you're within a single process like the list import example I was talking about before. But yeah, I'm not sure you want to update a 16 megabyte structure in memory and then persist it to disk every time I change 3 bits. You want to have a bunch of DBAs come looking for you? Try to persist that 16 meg structure into the database every time you change it. They will find their redo goes through the roof or it actually crashes Oracle. We didn't do that. And they will come find you and say, what the heck are you doing? Why are you you're only setting 8 bits in this thing, but because of a block size, I have to write all 16 megabytes. So doing this in a relational database is not smart. Doing this in a Cassandra or doing this in a Memcache or JBoss or any of these other caches where you have to read the whole structure, tweak it, and put it back. These are ridiculously expensive and it doesn't work. We didn't just talk about something that lets you manipulate bits on the server by just making a command, didn't we? All right, deletes. Every so often, somebody will look at this and go, OK, Bloom filters, great idea, but I want to remove something. I want to say that, OK, you really didn't see that ad, or I want to force you to see the ad again. If you go back and look at the picture here, I have no idea when this is all I have which keys set which bits, which is why the false positive problem comes in. So there's really no good way to remove from a Bloom filter. So again, the guys who get PhDs and stuff like that looked at the problem and said, well, we could go ahead and keep a few bits of counters for each bit in the Bloom filter and know how many keys hash to that. Well, I got a 16 megabyte filter to do my 10 million. I now need to add 4 bits on top of that. This is no longer as nice and efficient. It's no longer as space friendly. So what we started to do, and there's a bunch of folks out there also where we got this idea from, is we don't remove from a Bloom filter. Instead, we start building Bloom filters that have a very, very short lifetime. Again, Redis TTLs. So if I want to know you saw this ad in the last 4 hours, or you visited the website in the last 4 hours, I'm going to build 4 Bloom filters, each of which is only for an hour. I'm going to set a TTL on it so that at hour 5, this guy goes away. Redis magically makes it disappear. So now when I'm going to query and say, did you come to the website in the last 4 hours, I hit the 4 Bloom filters and I get an answer. I don't have to worry about, wow, if 5 hours ago you were here and you're not here anymore, so I've got to remove you from the filter. We just let the filters disappear. That mentality of building structures to let them deliberately fall away so you can ask the question yes or no is the key to failing fast in what I'm proposing. Any questions on that? So persistence. Kind of talked about this already, but I want to beat this one to death because we did look hard at, well, put this in Oracle. Or Oracle's got a bit set library that I can call. But do you really want to load a 16 megabit filter to check for 6 bits? Because if it's not in the SGA, you're going to page fault. You're going to call the I/O subsystem. It's going to go to the disk. It's going to pull it back up. It's going to find something in the SGA to throw away because you're probably beating your SGA up pretty good. To then ask a question of 6 bits. Now, yes, you can pin them. Yes, you can do all that stuff. But again, you're abusing a database. This is stuff that you really don't need in a database because I don't care about it n hours later. Or it's something that is highly read-only. So let's go ahead and pull it up into Redis. Oh, the last one's the fun one, the backups and replication. The DBAs had a pretty interesting comment as we were walking through this. Because we do transactional stuff in our database, we generate a lot of replication traffic to our DR site because Oracle doesn't know that that's a row that's going to be deleted and I don't care about in 5 minutes. He's going to blow it across the wire to the other part of the country, and we then pay for bandwidth, we pay for storage, we pay for all of that stuff for something that we don't care about in a few minutes. So why were we interested in Bloom filters? We found a lot of places where we went to the database to find that data didn't exist. Did you visit the website? Did you opt out of this? Did you download this white paper? In a lot of cases, the answers were no. We found a lot of places where we wanted to know if the user didn't do anything. And in the relational world, didn't is an index scan. Or hopefully it's just an index scan. It's not a read all the rows and find that there was nobody who actually did that particular event in the time period. So we're going, why are we doing all this I/O? Why are we doing all this work against the database when we can go ahead and hit the Bloom filter? So we started looking at persistent Bloom filters. About this time, Sentinel, the Redis HA implementation, became solidified and we became a lot more comfortable with it. So we started looking around. So we found a library on GitHub. The guy's name is Orestes and his project was called BloomFilter, that had done the hard work of figuring out how to use Redis for this. So we forked it, added what we call a population filter that I'll talk about in a few minutes, fixed a few bugs, and then pushed it back. Personally, this was the first time I've ever pushed back code to somebody who I have never ever spoken to. I've pulled other people's stuff into my GitHub repository, made changes, example code, all that. But this is the first time we pulled something down, played with it, got it working to be comfortable with it was, and pushed it back, and they accepted it. So right now, if you go look up, and there's a link at the end, this Orestes Bloom filter, there is code that we figured out and that we debugged in it, which I think is kind of cool. So benefits. The filters are stored in Redis. When I do this hash work, I should have put this picture in here multiple times. When I do this hash to figure out what my bits are, all I send over in a pipeline is the 3, in this case, the 3 bits I want you to look at. So for W, I hash on my, if I have an Oracle license, how many cores do you get? We keep coming back to that. I do my 3 hashes, send the request down to Redis. Redis goes, okay, set, not set. I get an answer back, set, not set. I go, you're not a member. I'm done. I have not touched Oracle. I have not even left the boxes that have got really fast CPU with lots of RAM because we didn't worry about expensive disks under the covers. We built the boxes to be Redis. Lots of memory, lots of processors. And I know that W is not in my set. So I'm not going to go ask the database about you. I'm done. I'm going to show you an ad, or I'm going to kick you out, or I'm going to do whatever it was that I was going to ask the database about. And I just did it by hitting a Bloom filter in tens of milliseconds or less. I can do reads and updates of the filter from a set of application servers. I can have a Redis instance, 4, 5, 6 app servers sitting in front of it, processing a request that every once in a while hits Redis and says, hey, is this guy a member of the set? I don't have to replicate that 16 megabytes everywhere. I don't have to worry if I change those 16 megabytes in server A, how am I going to replicate those 16 megabytes to the other servers? It's all sitting in Redis. Redis is taking care of persistence for me if I want it. Yes, there's a cost, and even if we do this in MySQL, there's still a cost. Because I did a presentation one time and somebody goes, oh, but just stick it in MySQL, that's free. Yeah, no, it's not. Because a 15K RPM disk that you would need to make MySQL performant is not cheap. Versus a Redis cluster that has almost no disk in it, that's nothing but RAM, I can get for a cost of about 3 15K disks. So while a free MySQL or whatever database is out there, this is not an appropriate thing to do in a relational database. The other thing is I can create a Bloom filter offline, load it up into Redis and start using it. So go back to the ad banner guys. If I had a problem where I needed to do crunching that was just not efficient for me to do in real time, I could still do that in Hadoop or Spark or XD or whatever else out there. Build a Bloom filter, shove it up into Redis, and then all my apps now have access to the latest data. So back to for the cost of for the cost of an Oracle license. I've mentioned that several times, but that's what drove us down this path. Thousands of filters. Now we pick 1 million elements just as an example. We have logic that looks at what our clients are doing, roughly guesstimate plus like 30%, how big those filters should be and build an appropriate size filter. So if you're one of my clients who only has 50,000 contacts in your database, we're not going to build you a 1 million element filter. We'll probably build you a 65,000 element filter. Then we're down into the 1, 2 megabyte range. So we can generate thousands of filters with ease. Set TTLs on them and let Redis blow them away. And have dozens of Redis instances which the front end shards to know which Redis instance he needs to talk to. So we have an organization ID that we hash and that tells us which of the Redis guys to go look up and talk to. Yes? So the question is, have we found the time to live feature to be reliable? Yes, we have.
How accurate as far as?
I think you can only set it to a second. I don't think we've ever gone and looked to see if, n seconds later it's still there. To the question.
Kind of the issue that we run into, we have fairly short time to live, and we found ourselves having to do like a double check.
Well, in the model, the way we use Redis, if the filter stays out there, it doesn't matter because I'm never going to go look at it. My filters are named, in the example that we were using before, named after an hour. So the app tier goes, okay, it's now 9 o'clock, go pull the previous 4 filters. If the 5th filter is still sitting there for another minute, it doesn't matter to us. If it was still there an hour later, we might have a problem because we might run out of memory. But we try not to run that close to the top line with the memory. And to the question before about whether we pin to CPUs, one of the threads that Redis does in the background is to go look for TTL things to drop. So pinning a particular core means that the thread that is looking to go do that cleanup is the same is the same core that is trying to do your processing. And that's why you don't want to pin to a core, you want to pin to a CPU. Any questions so far? All right, time. Oh, I forgot about this one. So one of the things that we're SaaS, multi-tenant environment, tens of thousands of clients. We have a finance department who likes to close the books as quick as possible. So they said, hey, we need to understand how many distinct users per month each client has had. Oh boy, thousands of clients, 12, 15 users per client, could have logged in once that month, could have logged in 50 times during that day. They want us to count them once. Okay, Hadoop, right? That's a big data. Chuck it off on the side, let it run for a couple hours. Here's your answer. Well, the chuck it off on the side, let it run for a couple hours is a very expensive thing if you don't have a Hadoop cluster for other reasons. So we looked and said, Bloom filters, error rates. What if every time a user logs in, we hit the Bloom filter with an update? We don't ever query it, we just hit it. And say, here are the 3 bits I want you to set for this user. And in the response that comes back from Redis, he's going to say if he said any of them. And if he said any of them, we haven't seen you this month, I'm going to increment my counter. I suddenly have the ability to, in seconds, if not fractions of a second, I don't think we've run a metric on this one yet, when finance says, okay, it's 1 minute after 12 on the first of the month, I need my data to go close my books, we hit thousands of Redis, just basic keys that have nothing but a counter in them. And that tells you, for that client, how many unique users they had this month. You guys want to have some fun with a finance person? Sit down with a couple beers and say to him, how long does it take you to close your books every month? And they'll tell you a couple hours, couple days, depending how big they are. And say, so if I could take an hour off of that, how much would you pay? You would be shocked by what they will agree to pay to if you can take hours to days off of their monthly close. And in our world, being able to give them the number of users so they can start the billing process in seconds is a huge deal. Put your engineer hats on and go talk to a finance guy. You might find that you know something that would help them close the books because you can apply parallel threads. And then suddenly finance becomes your friend. And when you want to go buy the other servers, you go, hey, dude, I helped you close the books faster. Buy me a server. Anyways, tangent, because my brother's in finance, and he and I, over quite a few beers, talked about this and realized that multi-threading a book closing process is something that we're going to see soon if it has not already happened with the cloud. Anyway, so back to this. Now, there are mathematical methods of estimating the size of a Bloom filter, a population looking at the Bloom filter. But again, I've got tens of thousands of clients, and reading the filter in to run this mathematical operation on it to figure out a count at the end of the month, that just wasn't worth it. So we do what we call population Bloom filters. Push this back, and they've incorporated it into that Orestes Bloom filter open source project. Questions before I get into some examples? Because I found sometimes explaining with examples that people understand, it makes this a little bit easier to understand. All right, so first one, web cache. So what URLs are already in the cache on another server? I'm the server. I've gotten a request from a client to go do something. There are 4 other servers in my cluster. I hash the URL with my server, hit Redis, hash the URL, hit the Redis Bloom filters for the other 3, and if they come back positive, I know somebody else has got it. I redirect them to that filter, to that web cache. No database lookups, not a lot of communications between the apps here because they are all keeping their own Redis-backed Bloom filters out there. All I have to know is which keys to go ask. P2P network, same idea. Which node contains which part of the file? So I'm a client and I say, oh, I need part 16 of the Avengers movie. Who's got it? Go hit a bunch of keys to see who's got it and go ask. I don't have to chat or you got it, yeah, you got it. No, I know exactly where the key is. Where that part of the file is. I go and I ask for it. Databases. Does this key actually exist on this page? HBase does it. Somebody mentioned Cassandra does it. The idea here is before you run the I/O, you build, basically the tools are building Bloom filters in memory so that when the question is asked, is this key available, where is this key? They don't go and read a block off of disk to say, are you in there, are you in there, are you in there? This is important in HBase because HBase, which sits on top of HDFS, is write once. I can't go in and change it. You basically write it once and I'm done. And if I have to say, do you have the latest value? Do you have the latest value? Do you have the latest value? That's a very expensive operation to find a piece of data. Instead, they have a Bloom filter that says, do you have this key? No, I don't. Do you have this key? No, I don't. Ah, yes, I do. I go and ask him. I don't go and ask each of these blocks because there are no data structures native to HBase to do this. Many, many RDBMSs use this under the covers. What's sad is none of them expose this to the user as a data type. I think this would be an awesome thing for some relational database to support and figure out the problems with the read it into memory to write 3 bits back. They're obviously doing it in their own internal data structures. Give me that data structure. Ad networks, the old way. We talked about this one already. Big Hadoop job runs, build the Bloom filters, and these Bloom filters are in the 200-300 megabyte ranges. There was a gentleman in here who years ago worked for, I think it was Fox, who usually comes to these meetings. I was kind of hoping he was here to give us some anecdotes of the way the ad networks used to do this. But he was the guy I first heard about Bloom filters for. They were building 200 megabyte BloomFilters and loading them up into Tomcat across a ton of servers in order to really quickly serve ads. So has the user been here this month? We've already talked about this one. So if they haven't, let's show them a message. Here, a false positive doesn't matter. If I already shown you the, hey, we're going to be down next weekend message, and I show it to you again, who cares? Blacklists and whitelists. If any of you have ever had to deal with people who are going out of their way to break into your systems, you know what this is all about. So we get a bad IP. This guy's been scripting us, been continually trying to log in, trying to guess passwords. Yes, you can drop something at the firewall, except for that knowledge is now at the firewall, it's not at the app tier. You don't have a way of going to an end user and saying, oh, we blocked you because that's the IP you came across, because you're blocking at the firewall. So what we do, or you could do, we haven't done this one, but this is an example I saw in a presentation. You put the known bad IP addresses into the filter. When you get your login request, you hash the IP and you hit the filter. If you're in there, ooh, bad IP, maybe. Remember, false positives. Rejecting a client because they hashed to a bad IP when they're coming from your biggest Fortune 5 client is not good. So here's where product's going to go, no, we can't accept that. So what you do then is you take the IP and you actually hit the expensive database and say, is that a known bad address? No, it's not. Log it, because you got to figure out how to change your hash function so you don't keep doing this to your best client. But if you are a good IP, you hit the filter, you're not in there, great, go right through. I haven't hit the database, haven't touched the database. These days, the ad networks do it with real-time updates. So as you're visiting a website, they are tweaking the bits for your session, just like we talked about before. So they're doing real-time BloomFilters. I don't know if they do it Redis-backed. I couldn't get an answer out of the few people I know, because that is a cutthroat industry. They don't like to talk at all about how they do their magic. Here's one that we do have a problem with that we're going to use, or we are using this for, client-side joins. So all your NoSQL databases out there, your Mongos, your Cassandras, your HBases, your fill-in-the-blanks, do not like joins. But you have to join the data together eventually. Oh, client-side join. Go Google client-side join. You'll find lots of people talking about it, but very few algorithms, very few discussions about how to do it. Challenge we've got right now. Architecturally, we may have multiple data stores. So you pick the right data store for the problem, but now you need to query across all of them to get an answer. So here's my Oracle, here's my Mongo, here's my soon-to-be DB2. And I need to combine them all together to find information about this contact. How do I do that? So you start to keep a population Bloom filter by unique user, in our case, by time. So if my query is, I need to find all of the people who visited the website, saw the ad, downloaded this white paper yesterday. Very reasonable query. Oracle, Mongo, DB2. How am I going to do that? Well, if I've got a Bloom filter that I can ask those 3 data sources and say, yesterday, do you have this contact in you? I can very quickly know I don't have to go to that data source. So that contact is not in Mongo, or that was DB2. It's not in DB2. Ooh, it's not in DB2, so don't even bother asking DB2 because he's going to say no. Well, okay, he's in all 3. Ooh, he's in all 3. Well, how do I drive? Where do I go first? Well, I can look at my population counts and say, I've only had 50 events of white paper downloads yesterday. I've had, I don't know, 8,000 of this and 10,000 of that. Pull the 50 first. Take those 50 as my keys to then hit the other 2 data sources. I don't read 10,000 up. Call Mongo with 10,000, call DB2 with 10,000. I read 50, call Mongo with 50, yes or no, call Oracle with 50, yes or no. Suddenly, I have reduced the amount of work, the I/O, the CPU, that I have to do for a client-side join because I've kept some data around. Does that make sense? Any of you got a problem where you're going, ooh, this would be really useful? I am failing fast. I am being able to say, no, don't go hit that database. Or I'm saying, look, take a subset of the data that you may have had to go look up and use these keys to go get it because I'm building some data structures in Redis with BloomFilters. All right, last part, fail fast. It's the ability to quickly know not to do something expensive. What could you do if you could say, I don't need to go to Oracle. I don't need to call this API. I don't need to do whatever. How quickly can you change and get back to your your end user and say, hey, here's the new web page, or here's the ad, here's the login, the whatever. Think about ways not to do work. I know we're lazy, we're engineers, right? We get into engineering because we're lazy. But really start to think, what can I do to not have to do work? Now, of course, I got to do a little bit of work to not do work later, which is one of the challenges here. And the cost of that Redis server is, in some cases, orders of magnitude, depending on how much disk you want to stuff in it and what kind of database, cheaper than a database server, where all you were using the database server was because it was there. I've got the MySQL, I've got the Oracle, I'll just dump everything in there. But the operational costs of doing that are becoming prohibitive. And again, Oracle license, and we're not going to get into that. All right, I have to put this in here. Once you get your head around this, everything looks like a nail that I can crush with a Redis Bloom filter. Be careful, because sometimes the cost of building and maintaining these structures is nowhere near what you're going to save. There are times when, you know what, just hitting the database because they've pinned that particular table, just deal with it. Don't build these filters and worry about TTLs and worry about all this stuff because it's cool. But there are definitely times where this fits. So what we did is we have instrumented the heck out of this tier. Anybody not know what Coda Hail is? Oh, okay. Used to be called Yammer Metrics. Gentleman, his name is Coda Hail, wrote a very powerful library that makes it trivial for you to instrument your code. So we have wrappers around if you matched, if you didn't match, how long it took to run the query to the back end, how many times did we actually go to the Oracle database, and how long did it take for the Oracle database, and just tons of metrics that Coda Hail makes exposed as JMX or as an HTTP request. Operations run something called Ganglia and Graphene, whoever said that, thank you. And then has alerts that says, hey, wait, we've got a certain percentage of misses this week, or the Oracle side is taking 50 milliseconds longer than it usually does, and alert people to go figure out something's wrong. This lets us look and say, wow, that tier we added with that nice Bloom filter, we get 90% of the time false positives. Guess what? Either change the filter or dump it. It's not worth it anymore. But you can't know that until you collect data. So collect data, collect data, collect data. All right, last one, a naive example of failing fast. So go back to our ad. I want to build a Bloom filter for the ads that are shown to a user. So I hash on user ID and the ad ID. That's what's in the Bloom filter. When the user visits, hash what ad I think I want to show them, because somebody in marketing has said, here's the top 5 ads, or these are the ads somebody's bought. And go ahead and hit the Bloom filter and see if the keys are already there. OK. If it was set, go ahead and increment the population count and display the ad. That way we can correctly bill somebody for the ads we've shown them. Now this is very naive because we're pushing data to Redis, asking it to do something an ad at a time. That logically makes sense because that was probably the way you'd approach it in a relational database unless you wanted to write some really complicated stored procs. But this is very naive. Let's do something with all of this cores we've got. Let's go ahead and hash the top 10 ads. And in a single pipeline, blow the 30 bits in our example over to Redis and find out which ones are set. Don't set them, just find out. The answer is going to come back and say, hey, they're all set, or none of them are set, or whatever the combination is. And I know which ad to now show to that user. I did one request to Redis. Now, when I say, OK, this is the ad I'm going to show them, I have to do a second request. But I've done 2 requests to look at the top 10 instead of 10 requests. So while it is blindingly fast, you still got to think about round trips. You still got to think about doing unnecessary work. You could also do this in Lua. But again, I'm not a big fan of Lua scripts, especially anything that may loop for a little while. Get in and get out is kind of my attitude with Redis. Here's a second example. We talked about this a little bit already. Let's go ahead and build a Bloom filter for each hour. So now I can sell an ad based off of how many times you've seen it in the last n hours. It's not today. So when you offer your ads up for sale, you say, hey, I will show this to a person once a day. Now, that's nice, but I'd like you to show it to somebody every 4 hours if they keep coming back. So I build 5 Bloom filters based on what you've seen, again for those 10 keys, and the TTL drops the one off the end, and my query is then against those 4 filters. Because I can request multiple, I can run operations against multiple keys in a single pipeline, I can ask Redis for those 30 bits in these 4 different keys and get answers back in milliseconds. Try to go ask your relational database, has this contact seen any of these reports, or these ads in the last n hours? And I'll see you in 100 milliseconds, 200 milliseconds, worse if you aren't really structured for that. I can do it in fraction or tens of milliseconds here. Another one. So I collect lots of data about my users. What virtual cows I have, what farmland I have, what chickens I have. So this has nothing to do with ads. Run a predictive model on the back end of things to do when the user shows up again. So say, hey, you haven't fed your cow, or hey, would you like to go pick up a new cow, or whatever the heck Farmville does. Go ahead and do this in Hadoop, or do this in some other tool that can crunch the data way faster, or a completely different group in your company that can crunch this data. Load the Bloom filter into Redis, and just go ahead and query as the people show up. You're not going back to a database. More importantly, I'm not keeping a database of what things should be shown to a specific contact. So if I've got 100 million users, Farmville scope, I don't want to do 100 million, or however many times 100 million inserts into a database to say, hey, this is the thing you need to show them next. I want to build a Bloom filter and have the business logic know that that Bloom filter means it's a cow. So instead of doing all of that redo, all of that replication across to the DR center, all I've got is a 16 megabyte Bloom filter that tells me whether or not I should offer this guy the chance to buy a cow. And in this case, a false positive, not such a big deal. If I offered to buy you a cow and you really don't need a cow, who cares? Query optimization, we already talked about this one. So the idea of using client-side joins, looking at a population filter, figuring out whether or not you even need to ask the data sources for the people who match this query. And in this scenario, instead of having a recipient identifier, or sorry, a cookie, I want to get everybody who visited the site yesterday and downloaded the white paper. So if I have to join all that together, this could be a pretty expensive operation. But again, I can look and say, visited the website 10,000 yesterday, downloaded the white paper 50. I'm going to take those 50 people and I'm going to push it through instead of running all of these queries and pulling the people up. Sorry, doing a select that pulls everybody up into memory and then try somehow to join them client side. I look at the population filter and say, here's a small number of folks. I'm going to use them. There is a risk with this one. If your query doesn't match to the size of your population filter, say your population filter is for a week, and somebody comes in and goes, I need a query for the last 11 days, you're going to pull some data for folks that don't fall within your 11 days and you got to throw them away. But in a fail-fast mentality, the fact that I only had to look at these people who maybe have been in the last 14 days instead of looking at a billion rows of contact behavior makes me is a much more efficient use of the databases. So conclusions. Data structure server. Get that into your head. If you can use this remote data structure server in a way that makes it easy for you to not have to go do an expensive operation, or if you have a business case which makes a lot of sense for twiddling things that are expensive to store. So twiddling bits, moving stuff between queues, standing up another JMS queue. If that's expensive in your world, think about using Redis as a database, as a data structure server. Bloom filters. Again, this thing's a hammer. We find so many places when we get in the mentality of, ooh, I'm going to fail fast where these apply. But there are times when we look at it and go, ooh, that was a bad idea. It's just not worth us to build this structure and carry them around for something that's already pinned in memory. Or that we hit 100% of the times when we hit the database. Just go ahead and let the database do it. And think as much as you can about how not to do something. Be lazy. Questions? Yes?
Yeah, I'm just trying to understand how Redis really acts on the so BloomFilter is a bit interface like one BloomFilter.
Yes.
So what exactly do you store in Redis? Like this a list of these bit arrays or by key by
Okay. Let me answer for the people. So the question was, what is actually in Redis when we're talking about these BloomFilters? What's in Redis is a character string of however many characters wide we tell it to be. Now, Redis allows you to very easily manipulate the bits. So when I go back to my hash function, should have put this at the end too. This is a very small one. We build filters, think about 16 megabytes indexed by the bit. So bit, yep, it's a bit array per key. So that's what we have a bit per key. So in the example of I've got 4 BloomFilters, 1 per hour for file downloads, there's a key called file download 9 o'clock, 10 o'clock, 11 o'clock, 12 o'clock. They're independent keys. And this is where key explosion comes in. Thousands of these filters across thousands of clients, and all of a sudden my Redis instance has got tens of thousands to millions of keys. So this is where you build that dictionary, so ops can see what the keys are that are in there without. Yes, so if you're running 5 filters that are getting hit in parallel, you do. Because the update of those bits that you want, so if you have an app tier of 5 servers here and here's Redis, if you push a BloomFilter to here and he updates it, these guys need to see it because they're all sitting behind a load balancer. And if I have to replicate 16 megabytes across the 5 every time it changes, the network chatter and the latency is just going to be horrible. So you put it into Redis, they all talk to Redis. When the bits get changed, these guys don't care because their next query may not even look at those bits. Yeah, so again, data structure server. This idea of a data structure server is a pretty powerful concept. All right, so references. Any other questions? Yes.
Yeah, so mostly because there's a chance in your setup that you can actually end up with false negatives because of the issue with the asynchronous, and if you had a partition during a write and that server drops down, you'd have a miss. So a bit would have been set when it should have been set.
All of the bits would not have been set.
Sure, which would end up with a false negative, which is completely counter to how BloomFilters are supposed to work. But the nice thing about it is, if you could get this at a point where you know what CRDT is?
No, I do not.
So if you have a chance, look up CRDTs. They're commutative replicated data types. So a BloomFilter is a bit set would be a commutative replicated data type. Because your set operation is something that can be repeated against a BloomFilter, because you're not ever unsetting. So that's a comment I wanted to make from some issue that I saw with what you're doing right now, which could be fixed. And it would be great if Redis had it in it, then that'd be amazing. Then the other thing was for deletes, you generally just have a second BloomFilter that just collects the deletes. Is a good tool for actually storing the deletes. So if you see you read from one, that shows that the thing exists. If you read from the other thing, that shows that someone had come back through and deleted it. As long as you don't have things adding them back in.
Or if you're having a false positive where we both hash to the same key, you've removed me, and then I'm. Yeah. So yeah, to the folks on the video, the suggestion was made to handle the deletes, to go ahead and build a second parallel BloomFilter, and then add the contact or the cookie to that, so that when you want to remove somebody, if you hit the first one, you hit the second one, and if they're in there, there's a pretty good chance they've been removed. And then go do the expensive operation. Okay, I hadn't thought of that. It's a good idea. CRDTs? Okay, I'll look at it. For people on the video, gentleman in the audience said look at CRDTs as an idea for communicative replicative
Commutative replicative data types.
Communicative replicative data types.
They're guaranteed consistent eventually.
Okay, they're guaranteed. Oh boy, okay, we're not getting into eventual consistency.
The problem you have is you
I
have no
understand the
strong
problem.
consistency in Redis. So you need to actually have something that puts that strong consistency in there. Okay. If you're dealing with cluster, because you will have partitioning, especially if you're pushing this stuff out to AWS.
Yeah. Okay, good. It's good to know. We need to think through if that even applies to us, but that is a rule. References. I cannot get into GitHub for some reason today. I thought it was my work network, but I couldn't do it here. So I will eventually put those code samples up there. That's me on Twitter. This is already up on SlideShare if you want to look at it. And any other questions? Was this useful? Okay. I was a little worried because some of it's way up here, and if you don't have a problem that applies nicely to BloomFilters, we spent some time internally having to explain this to folks. I love our product team, but once we got their head around first fail fast and then around acceptable false positives, they just started to eat this up. Because when they realized the cost savings of not buying another Oracle core, they're happy. Well, thank you, everybody.